All right, class. I think their exam one retry, I think will open up Monday. All right. I don't know if I put an announcement about that yet or not, but if not, I'll have an announcement up later today. All right. So there's that. Since we missed class Wednesday, I'm going to try to change the due date for the WebWorks homework for this section, give you a little more time. Okay. But today we're talking about proving identities. So let's see, here is a chart. So far y'all have some identities. Y'all know the Pythagorean identities, right? And what is an identity? An identity is an equation where left-hand side is equal to the right-hand side, no matter what number you plug in to your variable. Kind of like x equals x. That's an equation, right? It's an identity because no matter what you plug in for x, both sides are the same. So y'all know these identities, right? We got them from the Pythagorean theorem. And if you divide everything by r squared, you get this. Or if you divide everything by x squared, you get this one. Or if you divide everything by y squared, you get that one. All right, so the Pythagorean identities. Then you have your even and odd identities. Right, these are useful. So your even functions, you can throw this minus sign away, right? Odd functions, you can pull it out front. You all know those. Your reciprocal identities. All right. Sine is just 1 over cosecant and etc. So you should know those by now. I know they're kind of hard to remember, but by the time you're done with this homework, you will have these back to your mind at all times. And then your quotient identities. Tangent is sine over cosine, cotangent is cosine over sine. Right? And we use these to simplify stuff. So, for instance, they want us to show that this is an identity. So it might not be obvious that the left-hand side is exactly equal to the right-hand side, all right? But there's two kind of approaches here. We could start with one side. We'll say left-hand side. I'm going to replace tangent with sine over cosine. So you can see that, yeah, the left-hand side is equal to the right-hand side at all times. So this is an identity, all right? So sometimes you do start with one side and work your way to the other side. That usually works if one side is simple and the other side is complex, But sometimes both sides are hairy. So if we look at this, we have three different trig functions going on here, right? So you can always turn things into just sines and cosines, right? You could have a big equation that has all six trig functions going on, right? Well, you can always do substitutions and reduce it to two, sine and cosine, or tangent and secant, or whatever you like working with the most. When I see something like this, there's no trig functions over here. How can I get rid of these trig functions? Well, first off, there's three of them. How about I simplify it and turn it into two different ones? I know cosecant is 1 over sine, and then I have times cosine, and I know tangent is sine over cosine. I see, okay, 1. Okay. Now what you need to do is stare at this for a while after you've done the identity, right? Stare at it a while and imagine imagine this in your head. Be like, okay, this is 1 over sine. This has a sine on top, so those sines are going to go away. This one has a cosine on the bottom, and it'll cancel that cosine. So after you prove an identity, you look at it a while, and then try to convince yourself in your head, right? So that this you get your brain wired, all right, to see this stuff without having to write out all the steps. Because the trick to this is being able to see several steps ahead, really, and then the motivations for it. All right, this thing, I see the argument here. This one has a minus in it, and this one doesn't. So that's the first step of making things simple is like, how about we make sure everything has the same argument? Everything is just x instead of negative x's. So I might be like, okay, the left-hand side, let's keep my 1 plus sine of x. And this, I am going to pull the minus sign out. All right. So now at least, because over here, I don't see any, there's no cosines of negative x, right? There's no negative x going on. So the first thing I'd want to do is get rid of that, right? I'm trying to match samesies here, right? So now everything's just x. And this is the difference of two squares. You're going to see stuff like this all the time. And you get what? 1 minus sine squared x. When you multiply that out, right? 1 minus sine squared. The minus sine x and the positive sine x go away. You see stuff like this. Anytime you see sine squareds or cosine squareds, here, I'm going to use shortcut notation. Sine squared plus cosine squared is 1. That's your Pythagorean identity, right? This is what you use more than anything else, is this guy. But of course, you could, let me do it this way. If I move the cosine over, right? So because of this, I can always turn sine squared into 1 minus cosine squared, or cosine squared into 1 minus sine squared, right? Just by moving one of these to the other side. So I can always replace sine squareds with cosine squareds because of this identity. And this happens to be a difference of two squares, right? So this being the difference of two squares is 1 minus cosine times 1 plus cosine. And this over here is 1 minus sine times 1 plus sine. So you're going to see stuff like this, like 1 minus sine. And when you see that, automatically start thinking Pythagorean theorem. Right? That's your most powerful tool right there. Okay. So when I multiply these out, I look at this and I think about this, and I'm like, okay, if I move sine squared over, then this is just cosine squared, which is the right hand side. Does that make sense? All right. All right. This problem, there's two different trig functions, secant and sine, right? Now, I could turn secant into 1 over cosine, but then I'd still have two different trig functions. Then I'd have cosine and sine instead of secant and sine. So that's not really going to simplify stuff, right? If I look at this, I could be like, okay, my left-hand side, if I changed out secant for cosine, all right, now I have fractions over fractions. It's not any more simple, is it? So maybe that might not be the best step to go. We could still do it. Let's see. If we did this, I would be like, well, this isn't a fraction at all. Over here, we have fractions over fractions. If I want to make this look more like that, um, instead of dividing by this 1 over cosine squared, I'll multiply by the reciprocal. So this would be the same as multiplying by cosine squared. This is just one thing, and then I see here two things. So if I distribute this, I get cosine squared over cosine squared, and then minus cosine squared. And it's like, well, this is one thing, and this is two things, but let's see, this is just one. And now when I see that, I say, oh, that is, right, because sine squared plus cosine squared is 1. If I move this over here, I see that this is just sine squared, which is the right-hand side. So that's one way of doing this, right? Let's try it a different way. When I see that, instead of going cosine, I might think, oh, that's going to give me fractions over fractions. That's just going to be more complicated. When I see a trig function squared minus 1, I automatically think Pythagorean theorem. But I can never remember the other ones. I know sine squared plus cosine squared equals 1, and I know there's two other trig identities, Pythagorean identities that have tangents and secants, but I can never remember what they are. So I always do this. Start here. And I'm seeing secant, and I know secant is what, 1 over cosine? So secant would be what, r over x? So I'm going to do this. So I get the r over x. So what do I have? I have 1 plus tangent squared is secant squared, right? So if I move the 1 over, I could see that this stuff being secant squared minus 1 is just tangent squared. And I have secant squared on the bottom. All right. I don't know. Now I'm dealing with three trig functions. I'm dealing with tangents, secants, and sines. But at this point, I'd look at this and say, well, this is a fraction. This isn't. How do I make this go away? Well, I have to get rid of this. That means I need a secant squared up here so that I can factor them, right? Or I could be like, I'm going to change things into sines and cosines. Screw it. Tangent is sine squared over cosine squared, and secant is 1 over cosine squared. So now instead of dividing by 1 over cosine squared, it's the same as multiplying by cosine squared. And that's the right-hand side. So I could do it that way. Or, how about this? If I looked at it and saw, how about I separate this? I have secant squared, left-hand side. Secant squared over secant squared minus 1 over secant squared. And break it up. And this is just 1. And then this is 1 over cosine. I mean, it's 1 over secant is cosine, right? And then I know from my Pythagorean identity, this is just sine squared. So there's three approaches, right? There's no one way to do these problems. And you might start off trying something out, and it might just get bigger and bigger and more complicated instead of more simple. And you might just be like, I give up. Don't throw that paper away. Don't erase your work. What you do is whenever it doesn't go where you want it to go, you write down first attempt, and then you try again, because you might try 4 or 5 different attempts that aren't panning out, and you're going to forget what you tried and what you didn't try. Okay. So again, there is no one way to do these. It's basically just navigating a maze. Now these are very simple problems, okay? Here, if I try to prove this, I could be like, this is a fraction, that's not. I got 3 different trig functions going on. Obvious approach to this would be like, okay, cotangent is cosine over sine, and then cosecant is 1 over sine. So instead of dividing by the fraction, it's the same as multiplying by its reciprocal, and that's my right-hand side. All right. So switching to sines and cosines is often a very helpful strategy. All right. not always the best, yes. This is the left-hand side, that's the right-hand side. So the left-hand side is this, right? And then I just replace cotangent with that, and I replace cosecant with this. Does that make sense? Yeah, is that better? All right. Uh, Here they say create an identity. All right, so if I'm going to give you a math problem and say prove this identity, well, how do I come up with that problem, right? I might start off with, I know that 1 is 1, right? And let's say I'm going to rewrite 1 as cosine over cosine, right? And I'm going to rewrite this one. On this side, I'm going to add sine and subtract sine because that's just 0, right? So I started off with this. I added some stuff. Okay, now I'm going to add sine to both sides. No, I'm not. Let's see. I'm going to multiply both sides by tangent. I could do that, right? And so now I have here, I'm going to take this over cosine here. This is tangent, and then I have cosine. I'm going to rewrite this 1 over cosine as secant. And over here, let's see, I'm going to distribute this tangent. So I have a tangent plus sine tangent, and then minus sine tangent. But I'm going to take this tangent and I'm going to write it on the bottom as cotangent, because tangent's 1 over cotangent. So I know this is identity because I started off with 1 equals 1 and I just added stuff. Does that make sense? That's how I would create a problem. This is a big old nasty thing, right? But I know it's an identity. I can't give you something that's not an identity and say, hey, prove this is an identity, right? I need to make sure that it actually works. So sometimes practicing stuff like this can help you develop the insight, right? Because it's going backwards is easy, if you've already done it. So let's look at this. They want this all in terms of sine, right? We paste this. Okay, well, tangent theta is sine over cosine, and then secant theta is 1 over cosine, right? So I have 2 sine theta over cosine squared. Well, they want everything in terms of only sine. Anytime you see cosine squared, you can turn it into sine squared because sine squared plus cosine squared is 1, right? So uh, if I move this over here, right, I know that I can rewrite as 1 minus sine squared. So yeah, problem solved. They wanted everything in terms of sine alone. That makes sense? Kinda? I know a lot of this looks like just like a blur, right? But it's not as hard as it looks. It's just remembering these basic identities, right? These basic identities, and especially these three. That's all you're doing is using those over and over again. And there's certain tricks, motivations, right? That'll help guide you. Let's look at this one. So I look at this, and this looks complicated. This is a fraction. This isn't. You know, that's something we have to resolve. The main thing that sticks out to me is that we have these negative thetas. There's no negative thetas over here, right? So that's the first thing I'd want to resolve. I'd say, okay, the left-hand side, this, right? I'll use my odd and even identities, right? Sine is odd. That means I can pull the minus sign out, right? But since it's squared, I do that for both of them. So I'm getting two minus signs pulled out, and they're going to cancel with one another. Does that make sense? Yeah, kind of. Sine of negative theta is identically negative sine of theta, right? But this is squared. So if I square both sides, then I get what? Sine squared of negative theta. This minus sign gets squared and goes away. So I'm going to replace this with just sine squared theta. Cosine is even, so that means I can just throw that minus sign away. Here I can pull the minus sign out, and then this one I could throw away. Okay, so now it's a little bit more like this. There's no negative thetas, right? This is no negative thetas, so that's the first thing you want to do. But now it's like this is a fraction and this isn't. So somehow I need to get this up here as well so that it'll factor out, right? So to make this go away, I need to be able to cancel this, but I can only do that if it's on top. Well, this is the difference of two squares, so I could write that as sine theta minus cosine theta times sine theta plus cosine theta. And both of these are negative, so I'll pull out a minus here. This is sine theta plus cosine theta. So now I can see, aha, there's that guy. I can get rid of it. Now it's not a fraction anymore. But this minus sign has to go somewhere. So it's going to go up here. So this is negative sine theta plus cosine theta. Well, that's exactly what we have here on the right-hand side. So we showed the left-hand side is equal to the right-hand side. Yes. This one? Yeah. Well, cosine is even, so that means this minus sign you can just throw away. All right, the even ones, the minus sign, you just throw it away. Because remember the graph of cosine looks like this, right? If I go over here, I get this value. If I go the opposite direction, I still get the same thing, right? If you fold it over the y-axis, it matches. Going to the left, you go to the right, it looks the same. All right, here, both sides look complicated, right? Now, every problem I've done so far, I started at the left-hand side and worked my way to the right-hand side. You don't have to restrict yourself like that. You can work with both sides, right? Remember how I do like this? I'd be like 2, let me see, x squared plus 2x plus 1 equals 7. And I'd say, well, that's the same thing as if I factored this is what, x plus 1 squared, right? That symbol means logical equivalence. It means these equations are exactly the same thing, right? We can use that symbol. We can work with both sides at the same time. I could say this equation logically equivalent to, I don't know, I'll just start trying to simplify both sides at the same time. I can do that. I'm looking at this and I'm seeing two trig functions, right? Sines and tangents. What can I do here? One thing I'm looking at is I see tangent on the bottom everywhere, right? So one thing I'm going to do is I'm going to factor out tangent. Okay. So this is an identical equation. These are logically equivalent. All I did was factor out tangent, right? And looking at that, I could be like, okay, well, I'm gonna multiply both sides by tangent, right? I can multiply both sides of an equation by a number, right? Or anything I want, and I get a logically equivalent one. What that does is lets me get rid of that. So now I'm just looking at sine squared theta minus 1 over sine theta minus 1 equals sine theta plus 1. So instead of all this, I showed it's the same thing as just this. That makes sense? I worked with both sides at the same time. Can I handle that? A different approach. So now I'm looking at this. This one's a fraction. This one isn't. Where my minus here go? And theta minus. Yeah. So I got to get rid of that because this is not a fraction. Well, this is the difference of two squares. That's sine theta minus 1 times sine theta plus 1 sine theta minus 1. Right? So I could go boom, boom. Now I have the left-hand side is equal to the right-hand side. It's an identity. So that could be one approach, working with both sides at the same time. Let's try it a different way. All right, I'm looking at this, and let's try to just go from left-hand side to right-hand side. The left-hand side, at least this is a fraction and that's a fraction. Okay, they have that in common. I could turn everything into sines and cosines, right? Let's say I look at that and I'm like, I can replace that with cosine squared, right? Why? I don't know. I'm just gonna try stuff at random, right? See if it works out. This tangent is really bothering me. The fact that it shows up twice, I don't like repetition. That's needless complexity, right? You can always factor something out. So now it's not any simpler, right? Now I got three trig functions instead of just two, right? But let's go ahead and let's get rid of this tangent here. Let's replace tangent with sine over cosine. Okay, there we go. And how about this? There's no, I don't know, what am I going to do here? No, let's not do this. This is a bad idea. Why is that a bad idea? Because this has tangent on the bottom. I got tangent on the bottom. That's the one thing I want to leave alone, right? And this step, that was a bad idea too. Why? Because this guy has a sine theta plus 1 up there. So I don't want to turn this into cosine. There's no cosines over here, right? So the only step I took that was worth doing was this one, factoring out the tangent. Tangent on the bottom, tangent on the bottom, right? Samesies. So this, looking at this and that, how do I turn this into that? Well, difference of two squares. Much better to go sine theta minus 1 times sine theta plus 1. That's a more smart move, right? So now I can see, aha, I have that and I have that, right? So color coded. This is good. This is good. Oh, and look, the rest of that goes away. Which is exactly what we needed it to do because there's nothing else over here. So you see that one step instead of, what was our first approach here? Like, how many times did we do this thing? You know, you can either do it in 10 steps or you can do it in one step. And it's a matter of technique, right? Trying to make it look the same. Again, we focused on tangent, there's tangent. So let's get that tangent there. So it's the same. And we have this, we need to show that that's over here somehow, and then make everything else go away. To get this guy. All right, so here instead of working with both sides, this is already really simple, right? So we have to turn this into the number one. Our left-hand side, I mean, what could we do? We could say this is just sine squared, right, from our Pythagorean identity, right? Cosine squared to sine squared is 1. This looks like Pythagorean identity. I can't ever remember what that one is, so I'm going to do this again. Let's see, cotangent is x over y, right? So x over y. This identity is what? Cotangent squared plus 1 is, what is this? Cosecant squared, right? R over y, yeah. So, oh, I'm going to replace this with cosecant squared. Well, I know that cosecant squared is just 1 over sine squared, right? The right-hand side. So that would be my thought process for this, right? When I see stuff like that, I'm like, Pythagorean theorem. This is two things. This turns it into one thing. So I can turn these two things into one thing. These two things turn into one thing. Hopefully they go away. Here, this stuff, all they're saying here is that if you look at that, it resembles something like this, right? They're saying sine squared theta, or yeah, I'll do it like this. Sine squared theta minus 1. They're saying you might not recognize that as a difference of two squares, but you recognize that as the difference of two squares, right? Right? So you have your algebra, but the pattern recognition might not be clicking because we're writing stuff like this. But if you just called this x, you might be able to recognize your basic algebra more easily. So that's all they're saying here is that you can define. You could be like, I'm going to define sine theta to be x, and then I don't have to write sine theta over and over again. I can just call it x. You can call it anything you want. Call it rainbow unicorn. I don't care, right? That's all they're saying, and they're doing that because they're hoping that it'll jog your memory and allow you to see your algebra better. So like if you see something like that, you want to think 2x squared plus x minus 1, where x is cosine theta, right? Because y'all are used to manipulating expressions like that, right? Well, this is exactly the same thing. It just doesn't look like it. So again, a lot of this stuff you see a big fog of math, right? Your brains are wired to recognize this by now. So the goal is for you to see this and be thinking this. Bridge that gap. Does that make sense? I've never seen this put in any trig books, but I guess it's their motivation there. So this, when you look at this, you might not be thinking difference of two squares, right? But if you wrote it like that, maybe you recognize that as difference of two squares. Samesies, it's the same thing, right? This is 2 cosine theta squared minus 1 squared. And thus you can factor it. That's all they're trying to get you to see. Okay? Right? Difference of two squares. This would be 5 minus 3 sine theta. That's 5 plus, plus 3 sine theta. Right? Difference of two squares, right? This would be cosecant theta minus cotangent theta as cosecant theta plus cotangent theta. Do that one again. Yeah, I could do difference of two squares, but what else could we do with this? I could say, okay, this is, let's see, cosecant is 1 over sine, right? And then cotangent would be cosine over sine, right? So common denominator, this is 1 minus cosine squared over sine squared. Well, 1 minus cosine squared is sine squared. So this is all just 1. It's a fancy way of writing the number 1. Well, what good is that? Well, let's say I had an equation that was some big old pile of stuff, and on the bottom I had this to make it even more complicated. Whatever, I'm looking at that and I'm like, and then over here I have this same stuff, but it doesn't have that on the bottom. Well, because this is just the number 1, I can always just multiply by the number 1, right? Oops. I can multiply by the number 1 with my smart one. I can just put that there. I just multiplied by 1, and I just simplified things, right? This one here is fine. So look at this guy. Cosine over 1 plus sine equals 1 minus sine over cosine. It's like they just flipped it over and replaced the plus with a minus. Do those even look, I mean, they look kind of alike, but, you know, it's hard to see that that's actually an identity. So let's start with, we'll start with the left-hand side. Again, you can work with both sides at the same time if you want, right? Let's do it with both sides. Let's try, I'm going to just write down the same thing here, right? Identical equation. I haven't changed anything. And I might look at this and say, well, this one has a cosine on the bottom. Well, this one has a cosine on the top, and this one doesn't, right? So how about I multiply this thing by a cosine over a cosine? I could do that. I just multiplied by the number 1. And now I have a cosine on the top and a cosine on the top, right? I could try that, or I could be like, no, I'm going to multiply both sides of the equation by cosine. I can multiply both sides of the equation by anything I want, right? But now I got a cosine squared and only a 1 cosine, so let's not do that. Let's try this one. This has a cosine, this one didn't, so I gave it 1. So here we're going to try the process. Instead of making things simpler, we're going to add stuff until both sides are the same. We'll try that approach. Now let's see, this one has a 1 minus sign on the top, and this one over here doesn't. So let's see, I'm going to multiply this one by a 1 minus sine over 1 minus sine theta. Okay, so now the tops are the same, right? Okay, cool. Let's keep that since those are the same. Over here, I have cosine squared on the bottom. What is this? This is the difference of two squares, right? This is 1 minus sine squared, isn't it? and 1 minus sine squared is cosine squared. There, the left side is identical to the right side. So instead of making things more simple, I added stuff till I made both sides the same. Totally different approach, right? Different than what we were doing before. We were trying, let's make it more simple, more simple, more simple until we have 1 equals 1. Here we have a giant pile of stuff equals a giant pile of stuff, but it's the same pile of stuff. So we can do it that way too. Or we can follow their hint. They start at the left-hand side. We got a cosine theta over 1 plus sine theta. Okay, so what can we do to this? We can't simplify it at all, right? There's no squareds. We can't replace cosine squared with 1 minus sine squared or anything. But what we do see is over here, they have a 1 minus sine theta on the top. So let's give it a 1 minus sine theta on the top. And we can't just do the top unless we do the bottom. This is the number 1. So I saw this and said, well, it's not over here, so let's put it there. So I have cosine 1 minus sine theta, right? So this has 1 minus sine theta. We have 1 minus sine theta. We have this cosine. This doesn't have a cosine on top. So that means I'm going to have to try to get a cosine out of this so that they'll cancel out, right? Plus, they have a cosine on the bottom and we don't. So we need to get, we need to turn all of that into cosine theta. That's our goal. Okay, well, again, we can multiply these out. We get 1 minus sine squared theta. So now I'm looking at this. We have this in common. I have to turn all of that into a cosine on the bottom. Oops, I forgot my theta. Cosine theta. Well, luckily, Pythagorean theorem says this is cosine squared. And that's what we needed. So now we have this stuff. It's the right-hand side. So that's another approach. How comfortable are y'all with this? Hard, right? It'll get easier. It looks a lot harder than it is. The hardest part about this is you can be creative. There's not just the one way that you do it, right? Like almost all the other math you do is like, here's the one way you do it. Maybe there might be 2 ways you can do it, right? Well, here there's pretty much an infinite number of ways. This is where you actually get to use your creative mind, right? This is more art than math. It's more poetry, right, than an algorithm. We're not just applying an algorithm we memorized to get the answer. We have these tools, these basic identities. Those are our building blocks, and you can build your proof any which way you want, right? That's the end of the section. So I guess that's it for today, folks. Yes. Yeah, that's fine. What's the question? Tangent times cosecant 1 over f of x. And what do they want us to do? So they want f of x equals stuff in sines and cosines. Okay. Well, first thing I would do is flip both sides over, right? They want f of x by itself, right? So if you have an equation, you can always rewrite it by taking the reciprocal of both sides, right? So that's the first thing I'm going to do. I just flip this over and then I flip this over. And 1 over tangent is cotangent. And 1 over cosecant is sine, right? So now I got rid of the fractions. cotangent is cosine over sine, right? So this f of x is just cosine. So that's one way to do it. Or I could have been like, I'd have still done this just to get f of x by itself. And I could have done, well, tangent is sine over cosine, and cosecant is 1 over sine, right? And then I've been like, okay, this is 1 over cosine. Could do it like that. But any which way you want to do it. I think the first step is, a lot of people don't think you can just take the reciprocal of both sides of an equation, right? But I mean, you can kind of see it. You move this over here, and then you move this down here. Boop. Yeah, that first step's critical. All right. All right.